Welcome! In this session, we'll be tackling a fascinating graph-based problem titled Cheapest Flights Within K-Stops. Get ready to explore various approaches to solving this problem, including a brute force method and more efficient techniques. Let's dive in. In this problem, we aim to find the cheapest flight cost between two cities, given certain constraints. The cities are represented by integers from 0 to n1, where n is the total number of cities. The available flights are described in a list of triplets, where each triplet specifies the source city, the destination city, and the price of the flight. Alongside this, we are given the source city, the destination city, and the maximum number of stops allowed. The task is to determine the minimum cost to travel from the source city to the destination city, ensuring that the journey involves at most the specified number of stops. If it's not possible to make such a journey, the output should be -1. The input parameters include the number of cities, the list of flights, the source and destination cities, and the maximum number of stops allowed. These constraints ensure that the problem is well defined and manageable within the given limits. The output of the problem is a single integer, representing the minimum cost to travel from the source city to the destination city within the allowed number of stops. If no such route exists, the output should be -1. Let's consider an example to clarify. Suppose we have three cities, numbered 0, 1, and 2. The available flights are as follows: a flight from city 0 to city 1 costing 100, a flight from city 1 to city 2 also costing 100, and a direct flight from city 0 to city 2 costing 500. The source city is 0, the destination city is 2, and we are allowed at most one stop. The goal is to find the cheapest route from city 0 to city 2 under these constraints. To solve the given example, we evaluate the available routes. The first route is a two-leg journey, from city 0 to city 1 for 100, and then from city 1 to city 2 for another 100. This totals to a cost of 200 and involves exactly one stop, which is within the allowed limit. The second option is a direct flight from city 0 to city 2, which costs 500. Since we are looking for the cheapest option, the route 0-1-2 with a total cost of 200 is the optimal solution. Now, consider another scenario where the number of allowed stops is reduced to 0. In this case, only direct flights are valid. Thus, the only possible route would be the direct flight from city 0 to city 2, which costs 500. Let's explore another example to understand how the problem scales with more cities and stops. Assume we have 4 cities, numbered 0 through 3, with the following flights: from city 0 to city 1 for 100, from city 1 to city 2 for 100, from city 2 to city 3 for 100, and a direct flight from city 0 to city 3 for 700. The source city is 0, the destination city is 3, and the maximum number of stops allowed is 2. In this case, the cheapest route is to take 3 flights, from city 0 to city 1, then to city 2, and finally to city 3. The total cost of this journey is 100 plus 100 plus 100, which equals 300. Although there is a direct flight from city 0 to city 3, its cost of 700 is significantly higher, making the multi-stop route the better option. The problem imposes several constraints to ensure clarity and feasibility. The number of cities, n, ranges from 1 to 100. The total number of flights can be at most n times n1, which represents all possible directed flights between different pairs of cities. Each flight is defined by its source, destination, and price, where the source and destination are valid city indices and the price is a positive integer up to 10,000. There are no duplicate flights, and the source and destination cities for a given query are distinct. Additionally, the maximum number of stops allowed, denoted by k, is constrained between 0 and n1. Some edge cases include scenarios where no valid route exists, requiring the output to be -1, or cases where only direct flights are allowed due to k being 0. For larger inputs, the solution must remain efficient to handle the upper bounds of the constraints. To solve this problem efficiently, we can use algorithms that are well suited for graph traversal and optimization, such as Dijkstra's algorithm or the Bellman-Ford algorithm. Both approaches allow us to compute the minimum cost while considering the constraints on the number of stops. The key is to modify these algorithms to account for the stop limit, ensuring that the solution remains optimal while adhering to the constraints. By focusing on limiting stops during the traversal, we can achieve an efficient solution that works even for the largest allowed inputs. When solving this problem, one of the first approaches we might consider is a brute force method using exhaustive search. The intuition here is to explore all possible paths from the source city to the destination city, ensuring that each path has no more than k stops. To do this, we can represent the cities and flights as a graph, where nodes are cities and edges are the flights between them, with weights representing the flight costs. With this graph, we can use a recursive backtracking approach to traverse all possible paths, keeping track of the total cost along the way. While this might seem like a straightforward solution, the issue is that the time complexity grows exponentially. For a graph with v cities and e edges, this approach becomes infeasible when the number of cities or the maximum allowed stops is large. For instance, when the number of cities, n, is up to 100 and k can also go up to 100, this method simply doesn't scale well and is too slow for practical use. Therefore, we need a more efficient solution. To improve on the brute force approach, we can use dynamic programming, or DP, to solve the problem more efficiently. The core idea is to use a DP table where each entry, DP I, j, represents the minimum cost to reach city j with at most I stops. For the transition, if there's a flight from city U to city V with a certain cost, we update the table using the formula DP K V equals min DP K V DP K1 U plus price. Initially, we set the cost to start at the source city to 0, represented by DP 0 SRC equals 0, while all other entries are set to infinity. As we iterate through the stops from 0 to k, we update the table based on the current flights, gradually building up the solution. This approach has a time complexity of O, k asterisk e, where e is the number of edges, and a space complexity of O, k asterisk n, where n is the number of cities. However, it does have some drawbacks. For example, maintaining a table of size k asterisk n can be memory intensive, especially for larger inputs. Additionally, while it's an improvement over brute force, it still might not be the fastest option for sparse graphs, where only a few cities are connected by flights. A more optimized approach involves using a modified version of Dijkstra's algorithm, which combines elements of breadth-first search with a priority queue. This method allows us to efficiently find the cheapest path while adhering to the constraint of at most k stops. Here, we use a priority queue, or min-heap, to prioritize paths with the lowest cost. Each element in the queue is a tuple consisting of the cost, the current city, and the number of stops taken so far. At every step, we expand the city with the current lowest cost, updating its neighbors by adding new entries to the queue with the updated costs and stops. If a path exceeds the allowed number of stops, we simply stop expanding it further. This approach works well because it combines the efficiency of Dijkstra's algorithm, which prioritizes cheaper paths first, with the ability to enforce the k-stops constraint as part of the traversal. In terms of complexity, it performs well with a time complexity of O, e plus n asterisk log n, where n represents the number of cities and e the number of flights, and a space complexity of O, e plus n, to store the graph in the priority queue. Given the various options, we chose the modified Dijkstra's algorithm as the primary approach for this problem. There are several reasons for this choice. First, this algorithm is particularly well suited for sparse graphs, which is a common scenario in this problem since not all cities are connected. Second, by using a priority queue to prioritize cheaper paths, it avoids the inefficiency of exploring all possible paths, as in the brute force method, or the overhead of maintaining a large DP table. This makes it a practical and efficient solution. Additionally, it strikes a good balance between computational speed and memory usage, making it scalable even for larger inputs. When comparing the trade-offs, the brute force method is clearly too slow for large graphs, while the DP-based approach, although better, is still hindered by its memory demands. The modified Dijkstra's algorithm, on the other hand, provides a more balanced and effective solution for this type of problem. To summarize, the key insights that make this approach effective involve representing the problem as a graph and leveraging the efficiency of BFS with a priority queue. By prioritizing paths based on their cost, the algorithm focuses on exploring cheaper options first, which reduces unnecessary computations. Additionally, the k-stops constraint is naturally enforced by limiting the depth of the traversal, ensuring that we only consider paths that meet the problem's requirements. This method strikes an optimal balance between performance and simplicity, making it a highly effective strategy for solving the problem of finding the cheapest flight route within a limited number of stops. In this problem, we are tasked with finding the cheapest flight from a source city to a destination city with at most k stops. The graph consists of cities as nodes and flights as directed edges, where the weights of the edges represent the costs of the flights. To solve this, we first represent the graph using an adjacency list. This structure allows us to map each city to a list of its direct neighbors along with the costs of traveling to them. For example, given the flights 0, 1, 100, 1, 2, 100, 0, 2, 500, we construct a dictionary where City 0 has two neighbors, City 1 with a cost of 100 and City 2 with a cost of 500. Similarly, City 1 has one neighbor, City 2, with a cost of 100. This representation is efficient for lookup and traversal, which is critical for the algorithm we are about to explore. Next, we approach the solution using a recursive depth-first search (DFS) with backtracking. Starting from the source city, we explore all possible paths to the destination city. Along the way, we track the current cost and the number of stops made. If the number of stops exceeds k, we backtrack to avoid invalid paths. When the destination is reached, we calculate the total cost of the path and update the minimum cost if the new path is cheaper. The recursive process continues by exploring each neighboring city from the current city, adding the flight cost to the current path cost and incrementing the stop count. To ensure accuracy, we establish base cases. If the destination is reached, we return the accumulated cost, and if the number of stops exceeds k, we terminate the exploration. This approach ensures we only consider valid paths and systematically explore all possibilities within the constraints. Edge cases must also be handled carefully. If no flights exist between the source and destination, we return -1. Similarly, for disconnected graphs where the destination is unreachable, the algorithm ensures that -1 is returned. To prevent cycles, we track visited cities and avoid revisiting them within the same path. Let's walk through an example. Given 3 cities and the flights 0, 1, 100, 1, 2, 100, 0, 2, 500, we start at City 0 with an initial cost of 0 and 0 stops. The graph is represented as an adjacency list, where City 0 connects to Cities 1 and 2, and City 1 connects to City 2. From City 0, we explore its neighbors. First, we move to City 1, accumulating a cost of 100 and incrementing the stops to 1. From City 1, we continue exploring and reach City 2, accumulating a total cost of 200 with 2 stops. This forms a valid path since the number of stops does not exceed k. Alternatively, from City 0, we could directly explore City 2, accumulating a cost of 500 with just 1 stop. Comparing these two paths, we find that the minimum cost is 200. To implement this efficiently, we use several key data structures. An adjacency list is used to represent the graph, allowing quick access to neighbors. The recursive stack is used to track the current city, the path cost, and the number of stops during DFS. A variable is maintained to store the global minimum cost, ensuring we always have the cheapest valid path. To optimize the search, we prune paths by terminating exploration early when the number of stops exceeds k or the current path cost surpasses the known minimum. In disconnected graphs, if the destination city is unreachable, the algorithm will return -1. The time complexity of this brute force approach is O, n caret, k plus 1, as each city can lead to multiple recursive calls up to k stops deep. The space complexity is O, k, reflecting the maximum depth of the recursive stack. To improve performance, we can use optimizations such as memoization to cache intermediate results, avoiding redundant calculations for the same city and stop count. An even better approach is to switch from DFS to breadth-first search, BFS, which naturally explores paths level by level and limits stops to k without additional pruning. These optimizations make the solution more scalable for larger graphs. While the brute force approach demonstrates the core concept, the optimized methods are essential for handling real-world scenarios efficiently. This implementation solves the LeetCode problem number 787, cheapest flights within k stops, using a graph traversal approach with a priority queue. Here's the detailed explanation. 1. Graph representation. The input provides flights as a list of edges. We first construct an adjacency list graph where each node, city, points to its neighbors and the associated flight costs. This is efficient for traversal. 2. Priority queue. A min-heap priority queue is initialized to store tuples of the form cost, current_city, remaining_stops. The heap ensures that we always expand the cheapest path first, which is crucial for finding the cheapest flight. 3. Heap initialization. We start by pushing 0, src, k plus 1 into the heap, representing 0 cost, the source city, and the allowed number of stops, k plus 1 because the source city itself does not count as a stop. For BFS with priority queue, while the heap is not empty, extract the cheapest path, smallest cost, from the heap. If the current city is the destination, DST, return the cost since we've found the cheapest path. If we still have stops remaining, stops 0, we iterate through the neighbors of the current city. For each neighbor, calculate the new cost and push the updated tuple, new_cost, neighbor, stops 1, into the heap. 5. No valid path. If the heap is exhausted without reaching the destination, return -1 to indicate no valid path exists within the allowed stops. This approach uses a combination of Dijkstra's algorithm and BFS, tailored for the k-stops constraint by keeping track of remaining stops in the heap. The use of a priority queue ensures that the algorithm efficiently finds the cheapest path. The overall time complexity is approximately O(e) plus n log n, where e is the number of edges, flights, and n is the number of cities. Here, we start by defining the class and method to solve the problem of finding the cheapest price within a limited number of stops. First, we create an adjacency list to represent the graph, where each city points to its neighboring cities along with the flight cost. This is done using a hash map, where the key is the city, and the value is a list of arrays containing the neighboring city and the associated cost. Next, we initialize a priority queue, which will act as a min-heap. Each entry in the heap is an array that represents the current cost, the current city, and the remaining number of stops. The heap is sorted based on the cost to ensure that we always process the cheapest path first. We then add the starting city to the heap with an initial cost of 0 and the total allowable stops, which is k plus 1 because the source city itself is not counted as a stop. The main logic is implemented using a while loop, where we repeatedly process the city with the lowest cost. If we reach the destination city during this process, we immediately return the cost because we found the cheapest path to the destination. If the destination city is not reached, we check if there are any remaining stops left to explore further paths. When stops are available, we iterate over the neighbors of the current city from the adjacency list. For each neighbor, we calculate the new cumulative cost by adding the flight cost to the current cost. We then add this information to the priority queue, including the neighbor city and the updated count of remaining stops. This ensures that all viable paths are considered while still prioritizing cheaper options first. Finally, if the while loop ends without finding a valid path to the destination, we return -1, indicating that it's not possible to reach the destination within the given constraints. This approach efficiently balances the need to explore different paths while keeping the computational cost in check using the priority queue. To solve this problem, we need to find the cheapest price to travel from a source city to a destination city, but with the added constraint of having at most a certain number of stops. The flight network is represented as a graph, where cities are nodes and flights are edges with weights corresponding to the flight costs. Because we want to explore the cheapest paths first while keeping track of the number of allowable stops, we use a priority queue, or min-heap. This approach shares similarities with Dijkstra's algorithm but is adapted to handle the additional constraint of limiting stops. For example, consider a network of 4 cities with flights and costs as listed. Our source is city 0, destination is city 3, and we can make at most 2 stops. First, we construct an adjacency list to represent the graph. The adjacency list groups all outgoing flights from a city, showing their destination and cost. For this example, the graph is constructed as shown, with each city mapping to its list of flights. Next, we initialize the min-heap with a tuple representing the starting point, a cost of 0, the source city, and the total stops available, which is k plus 1. In this case, the heap starts as 0, 0, 3. We then begin processing the heap. First, we pop the entry with the smallest cost. Here, it's 0, 0, 3, meaning we're at city 0 with a cost of 0 and 3 stops remaining. From city 0, we have 2 possible flights, to city 1 for a cost of 100 and to city 3 for a cost of 500. We push these options onto the heap, which now contains 100, 1, 2, 500, 3, 2. Next, we pop 100, 1, 2, meaning we're at City 1 with a cost of 102 stops left. From here, there's a flight to City 2 for a cost of 100, so we push 200, 2, 1 onto the heap. The heap is now 200, 2, 1, 500, 3, 2. Continuing, we pop 200, 2, 1, which represents City 2 with a cost of 201 stop remaining. From City 2, there's a flight to City 3 for another 100, so we push 300, 3, 0. The heap becomes 300, 3, 0, 500, 3, 2. Finally, we pop 300, 3, 0, reaching the destination City 3 with a total cost of 300. Since we've reached the destination, this is our result for the given input. Now, consider a different case where no valid path exists. Here, we have 3 cities with flights as listed. The source is City 0, the destination is City 2, and we're allowed 0 stops. First, we construct the graph using an adjacency list, which maps each city to its outgoing flights. For this example, the graph looks as shown. We then initialize the min heap with the starting point, cost 0, City 0, and 1 stop available, since k plus 1 equals 1. The heap begins as 0, 0, 1. Next, we process the heap. We pop 0, 0, 1, which means we're at City 0 with a cost of 0 and 1 stop remaining. From City 0, there's a flight to City 1 for a cost of 100, so we push 100, 1, 0 onto the heap. The heap now contains 100, 1, 0. Then, we pop 100, 1, 0, meaning we've reached City 1 with a cost of 100 but no stops remaining. Since there are no stops left, we cannot proceed further to City 2, and the algorithm terminates without finding a valid path. In this case, since no valid path exists from the source to the destination within the allowed number of stops, the output is -1. This result indicates that it's impossible to reach the destination under the given constraints. This example highlights how the algorithm respects both the cost and stop constraints during its traversal, ensuring paths that exceed the stop limit are not considered even if they might lead to the destination. Finally, let's look at a case where taking a direct flight is cheaper than making stops. Here, we have 3 cities with the listed flights. The source is City 0, the destination is City 2, and we can make at most 1 stop. First, we construct the graph, resulting in the adjacency list as shown. We initialize the min heap with the starting point, cost 0, City 0, and 2 stops available, k plus 1 equals 2. The heap begins as 0, 0, 2. We start processing the heap by popping 0, 0, 2. At City 0, we have 2 flight options, to City 1 for 300 or directly to City 2 for 500. These are pushed onto the heap, which now contains 300, 1, 1, 500, 2, 1. Next, we pop 300, 1, 1, meaning we're at City 1 with a cost of 301 stop left. From City 1, there's a flight to City 2 for 100, so we push 400, 2, 0 onto the heap. The heap updates to 400, 2, 0, 500, 2, 1. Finally, we pop 400, 2, 0, reaching the destination City 2 with a total cost of 400. This demonstrates how the algorithm efficiently considers both direct and multi-stop paths, prioritizing the cheaper options while respecting the stop constraints. In this case, the output is 400, as the algorithm finds the cheapest valid path within the allowed stops. To analyze the time complexity of this solution, let's break down the key operations. First, we construct the graph using the given list of flights. Each flight, represented as a tuple of source, destination, and price, is added to an adjacency list. This operation runs in O(e) time, where e is the number of edges, or flights, in the graph. Next, the algorithm employs a min heap to facilitate a Dijkstra-like breadth-first search. Each city can be pushed into the heap at most once for each stop level, resulting in k plus 1 levels in total. In the worst case, there are e edges, and for each edge, both a push and a pop operation are performed on the heap. Since each heap operation requires O log p, where p is the number of elements in the heap, this step contributes a time complexity of O(e) * log e, in the worst case, assuming the heap size is proportional to the number of edges. Additionally, as cities are popped from the heap, their neighbors are explored. This step processes all edges and therefore adds another O(e) to the overall complexity. When we combine these components, the graph construction contributes O(e), the heap operations contribute O(e) asterisk log e, and neighbor exploration adds O(e). Together, the total time complexity becomes O(e) asterisk log e. Now, since the maximum number of edges, e, can be as large as O(n squared) in a fully connected graph with n nodes, this can alternatively be expressed as O(n squared asterisk log n). Turning to space complexity, the adjacency list used for graph representation takes O(e) space, as it stores all the edges. The heap, which can hold at most O(e) elements in the worst case, also contributes O(e) to the space complexity. Other variables, like the graph structure, heap, and some scalar variables, have negligible space requirements, typically O(1). Combining these factors, the overall space complexity for the algorithm is O(e). In terms of nodes, for a fully connected graph, this becomes O(n squared). Now, let's examine the best, average, and worst case scenarios. In the best case, when the source and destination are the same, the algorithm terminates immediately, resulting in a time complexity of O(1). The average case depends on the structure of the graph and the value of k, as the algorithm will only explore a subset of nodes and edges. This typically results in a time complexity closer to O(e) asterisk log e. In the worst case, where the graph is fully connected with e equal to n squared and k allows traversal of all nodes, the time complexity reaches O(n squared asterisk log n, and the space complexity matches O(n squared). Let's compare this optimized approach to a brute force solution. A naive method would involve exploring all possible paths from the source to the destination with up to k stops, which is computationally expensive. Using backtracking, the time complexity balloons to O(n caret k plus 1 asterisk k, making it exponential in terms of the number of nodes and stops. In contrast, the optimized approach leverages a heap and limits exploration to k plus 1 stops, avoiding redundant calculations. This reduces the time complexity to O(e) asterisk log e. The mathematical basis for this improvement lies in the use of the heap, where each edge contributes O log e due to heap operations, and this dominates the overall complexity. In summary, this solution achieves significant computational efficiency compared to brute force while ensuring correctness, thanks to graph traversal techniques inspired by Dijkstra's algorithm. When solving this problem, there are several common mistakes to watch out for. First, when using recursion, it's critical to define clear base cases. Without proper stopping conditions such as exceeding the allowed k-stops or reaching the destination, you risk infinite loops or incorrect outcomes. Another frequent issue is not accounting for cycles in the graph. Cyclic paths can lead to redundant calculations or infinite recursion, so it's important to track visited nodes or carefully manage the number of stops within the current path. Additionally, the choice of data structures can significantly impact performance. Using a standard list instead of a priority queue or heap, for example, can drastically increase the time complexity of shortest path calculations, especially when implementing algorithms like Dijkstra's. Finally, overlooking edge cases is another pitfall. Scenarios such as no valid path between the source and destination, disconnected nodes in the graph, or paths that satisfy the stop constraint but exceed cost constraints can all lead to incorrect results. Always test thoroughly to ensure your solution handles these cases effectively. Another common mistake is misunderstanding the k-stops constraint. It's easy to confuse at most k-stops with exactly k-stops, which can lead to implementing the wrong logic. Carefully interpreting the problem's requirements is essential. From an interview perspective, there are several insights to keep in mind. When representing graphs, using adjacency lists is typically more memory efficient and faster for traversal, especially with sparse graphs. For optimization, transitioning from brute force to more efficient solutions often involves memoizing intermediate results to avoid redundant calculations. Additionally, BFS is a strong choice for problems involving shortest paths with constraints like k-stops, as it naturally explores paths layer by layer. While Dijkstra's algorithm is another option, its default behavior doesn't account for stop limits, so it requires modifications to fit this problem. Lastly, it's important to weigh trade-offs. Brute force is simpler to understand but becomes impractical for large graphs due to its exponential complexity. Opting for optimized BFS or priority queue-based approaches strikes a balance between clarity and efficiency. This problem often overlaps with others in the same category, which can provide additional practice and insight. For example, LeetCode 787 itself focuses on the cheapest flights within K-stops. LeetCode 743, network delay time, involves finding the time it takes for information to travel across a network, which is another shortest path problem. Similarly, LeetCode 1631, path with minimum effort, and LeetCode 1514, path with maximum probability, also deal with pathfinding under specific constraints. Exploring these problems can help you recognize patterns and refine your approach. Speaking of approaches, brute force is the most straightforward method. Its advantage lies in simplicity, making it easier to implement and debug for small graphs. However, its exponential time complexity renders it impractical for larger inputs. BFS with a queue is a more efficient alternative. This approach processes paths layer by layer, ensuring that shorter paths are explored first. However, it requires careful bookkeeping to manage both the number of stops and path costs, which can add complexity to the implementation. Another effective approach is a modified version of Dijkstra's algorithm. This method is highly efficient for finding the shortest path, especially when cost constraints are involved. However, to make it work for this problem, the algorithm must be adapted to account for the maximum K-stops constraint, which can complicate implementation. Finally, dynamic programming offers a robust way to optimize overlapping subproblems, significantly reducing redundant calculations. While this approach can be powerful, it does come with trade-offs. It usually requires additional space and may be less intuitive to debug compared to other methods. Each approach has its strengths and weaknesses, so understanding the problem requirements and constraints is key to selecting the most appropriate solution. Great job! We've explored the cheapest flights within K-stops problem and walked through its solution strategies. Remember the key takeaways about using dynamic programming and refining brute force approaches. Thanks for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!